I want to tell you a little about why there are so many matrices that are low rank in the world. So as computational mathematicians, Gil and myself, we come across low rank matrices all the time, and we started wondering as a community, why? What is it about the matrices, the problems that we're looking at? What makes low rank matrices appear? And today I want to kind of give you that story, or at least an overview of that story. So for this class, X is going to be an n by n real matrix. So nice and square. And you already know, or very comfortable with, the singular values of a matrix. So the singular values of a matrix, as you know, are a sequence of numbers that are monotonically non-increasing, that tell us all kinds of things about the matrix X. For example, the number of non-zero singular values tell us the rank of the matrix X. And they also, you probably know, tell us how well a matrix X can be approximated by a low-rank matrix. So let me just write two facts down that you already are familiar with. So here's a fact that if I look at the number of non-zero singular values in X, so I'm imagining there's going to be k non-zero singular values, then we can say a few things about X. For example, X, the rank of X, as we know, is k, the number of non-zero singular values. But we also know from the SVD that we can decompose X into a sum of rank 1 matrices. In fact, a sum of k of them. So because X is rank k, we can write down a low rank representation for X, and it involves k terms like this. Okay. Each one of these vectors here is a column vector. So if I draw this pictorially, this guy looks like this, right? And we have k of them. So because X is rank k, we can write X as a sum of k rank 1 matrices. And we also have an initial fact that we already know, that the dimension of the column space of X is equal to k, and the same with the row space. So the col space of X equals the row space of X, the dimension, and that they all equal k. Okay, so there are three facts we can determine from looking at this sequence of singular values of a matrix X. Okay. Of course, the singular value sequence is unique. X defines that singular its own singular values. Okay. What we're interested in here is what makes X, what are the properties of X that make sure that the singular values have a lot of zeros in that sequence. Can we try to understand what kind of X makes that happen? And we really like matrices that have a lot of zeros here for the following reason. If X is, we say X is low rank, if the following holds, right? Because if we wanted to send X to our friend, we're imagining X is a picture where each entry is a pixel of that image. If that matrix, that image, was low rank, we could send the picture to our friend in two ways. We could send every single entry of X, and for us to do that, we would have to send n squared pieces of information, because we'd have to send every entry. But if X is sufficiently low rank, we could also send them, our friend, the vectors, U1, V1, UK, up to VK. And how much pieces of data would we have to send our friend to get x to them if we sent it in the low rank form? Well, here there's 2n here, 2n here numbers. There's k of them. So we'd have to send 2kn numbers. And we strictly say a matrix is low rank if it's more efficient to send x to our friend in low rank form than in full rank form. Okay? So this, of course, by a little calculation, just shows us that provided the rank is less than half the size of the matrix, we are calling the matrix low rank. Now, often in practice, we demand more. We demand that k is much smaller than this number, so that it's far more efficient to send our friend the matrix X in low rank form than in full rank form. Okay? So the colloquial use of the word low rank is kind of this situation, but this is the strict definition of it. Okay, so what do low rank matrices look like? And to do that, I have some pictures for you. I have some flags, the world flags. So these are all matrices X. These examples, because they're flags, happen to not be square. I hope you can all see this. But what the top row here are all matrices that are extremely low rank. For example, the Austria flag, if you want to send that to your friend, that matrix is of rank 1. So all you have to do is send your friend 2 vectors. You have to tell your friend the column space and the row space, and there's only, the dimensions are 1 of both. For the English flag, you need to send them 2 column vectors and 2 row vectors, U1, V1, U2, and V2. And as we go down this row, they get slowly fuller and fuller rank. So the Japanese flag, for example, is low rank, but not that small. The Scottish flag is essentially full rank. So it's very inefficient to send your friend the Scottish flag in low rank form. You're better off sending almost every single entry. So what do low rank matrices look like? Well, if the matrix is extremely low rank, like rank 1, then when you look at that matrix, like here, like the flag, it's highly aligned with the coordinates, with the rows and columns. So if it's rank 1, the matrix is highly aligned, like the Austria flag. And of course, as we add in more and more rank here, the situation gets a bit blurry. For example, once we get into the medium rank situation, which is a circle, it's very hard to see that the circle is actually, in fact, low rank. But what I wanted to do was try to understand why the Scottish flag, or diagonal patterns, are particularly a bad example for low rank. So I'm going to take the triangular flag to examine that more carefully. So the triangular flag, it looks like I'll take a square matrix and I'll color in the bottom half. Okay, so this matrix is the matrix of 1s in below the diagonal. Okay? And I'm interested in this matrix, and in particular its singular values, to try to understand why diagonal patterns are not particularly useful for low rank compression. And this matrix of all 1s has a really nice property that if I take its inverse, it looks a lot like getting close to Gill's favorite matrix. So if I take the inverse of this matrix, it has an inverse because it's got 1s on the diagonal, then its inverse is the following matrix, which people familiar with finite difference schemes will notice the familiarity between that and the first order finite difference approximation. In particular, if I go a bit further and times two of these together and do this, then this is essentially Gill's favorite matrix, except one entry happens to be different. Ends up being this matrix, okay? Which is very close to the second order central finite difference matrix. And people have very well studied that matrix and just know its eigenvalues, its singular values. They know everything about that matrix. And you'll remember that if we know the eigenvalues of a matrix like x transpose x, we know the singular values of x. So this allows us to show, by the fact that we know that the singular values of this matrix are not very amenable to low rank. They're all non-zero, and they don't even decay. So I'm getting this from, I rang up Gill, and Gill tells me these numbers. That allows us to work out exactly what the singular values of this matrix are from the connection to finite differences. And so we can understand why this is not good by looking at the singular values. So the first singular value of x is, from this expression, is going to be approximately like 2n over pi. And from this expression again, the last guy, the last singular value of x, is going to be approximately a half. So these singular values are all large. They're not getting close to zero. If I plotted these singular values on a graph, right, so here's the first singular value, the second, and the nth, then what would the graph look like? Well, I'll plot these numbers. I'll divide by this guy so that they all are bounded between 1 and 0 because of the normalization, because I divided by sigma 1 of x. And so we can plot them, and they will look like this kind of thing. Okay. This number happens to be here where they come to be pi over 4n, okay, which is me dividing this number by this number, approximately. Okay, so triangular patterns are extremely bad for low rank. We need things, or we at least intuitively think that we need things aligned with the rows and columns. But the circle case happens to also be low rank. And so what happened to the Japanese flag? Why is the Japanese flag convenient for low rank? Well, it's the fact that it's a circle, and there's lots of symmetry in a circle. So if I try to look at the rank of a circle, the Japanese flag, then I can bound this rank by decomposing the Japanese flag into two things. So this is going to be less than or equal to the rank of a sum of two matrices. And I'll do it so that the decomposition works out. I have the circle. I'm going to cut out a rank 1 piece that lives in the middle of this circle. Okay, and I'm going to cut out a square from the interior of that circle. Okay, and I can figure out, of course, the rank is just bounded by the sum of those two ranks. This guy is bounded by rank 1 because it's highly aligned with the grid. Okay, this is dark. So this guy is bounded by rank 1. So this thing here plus 1. And now I have to try to understand the rank of this piece. Now, this piece has lots of symmetry. For example, we know that the rank of that matrix is the dimension of the column space and the dimension of the row space. So when we look at this matrix, because of symmetry, if I divide this matrix in half along the columns, all the columns on the left appear on the right. So the columns, for example, the rank of this matrix is the same as the rank of that matrix because I didn't change the column space. Okay. Now I go again and divide along the rows. And now the row dimension of this matrix is the same as the top half because as I wipe out those, I didn't change the dimension of the row space because the rows are the same top bottom. And so this becomes the rank of that tiny little matrix there. And because it's small, it won't have too large a rank. So this is definitely less than if I divide that up. A little guy here, it looks like that, plus the other guy that looks like that, plus 1. And so, of course, the row space of this matrix cannot be very high because this is a very thin matrix. There's lots of zeros in that matrix, only a few ones. And so you can go along and do a bit of trig to try to figure out how many rows are non-zero in this matrix. And a bit of trig tells you, well, it depends on the radius of this original circle. So if I make the original radius r of this Japanese flag, then the bound that you end up getting will be, for this matrix, r 1 minus square root 2 over 2 for this guy. It's a bit of trig. Better make sure that's an integer. And then again, here it's the same, but for the column space. So this is me just doing trig. Okay, and that's a bound on the rank. It happens to be extremely good. And if you work out what that rank is and try to look back, you'll find it's extremely efficient to send the Japanese flag to your friend in low rank form. Because it's not full rank, because these numbers are so small. So this comes out to be like approximately a half r plus 1. So much smaller than what you would expect. Because remember, a circle is almost the anti-version of aligned with the grid. Right? But yeah, it's still low rank. Okay.